Start video.
Sandy stuck in the corner and I'm gonna be like, minutes.
15 minutes.
We need to get time to leave the room because there's a lecture afterwards. All right.
Cool. Do you want to just get started then?
Yeah.
Or do you want to do some introductions? I'll let you do some introductions. Minimize this thing. That's very long.
You don't need it.
Okay.
Are we good?
Yeah.
Okay. Hi everyone. I think there's some feedback.
Yeah.
We good? Okay. Hi everyone, good morning, and welcome to another installment of the ESRG seminar series. Today we have guest speaker, Dr. Andrew Walker from the University of Oxford. Andrew did his MSI at UCL, followed by a PhD in geology in 2004, in computational studies of point defects and dislocation and force strike and its implication for the rheology of the mantle olivine at the Davy Faraday Research Laboratory. Then he went on to hold several prestigious postdoctoral positions, including posts at the Australian National University, the University of Cambridge, UCL, and the University of Bristol. And then following his stint at the University of Bristol, Andrew was a NERC Independent Research Fellow at the University of Leeds, where he then became an associate professor in computational geoscience. He then moved on to the University of Oxford in 2020, where he is now a senior research lecturer in computational geoscience. Andrew is actively involved in developing and maintaining several software packages aimed at tackling earth science problems, and he is involved in several exciting research projects from atomic to whole mantle scales. These include studies on mantle upwelling, modeling palisite meteorites, as well as core-focused research, including his research on how and when the inner core crystallized in order to solve the core nucleation paradox, which is what Andrew will be speaking to us about today. And with that, Andrew, please take it away.
Okay, so firstly, thank you for the introduction. What I'm actually going to talk about today is a problem in nucleation in the core, but it's not about the nucleation of the inner core. It's about nucleation of a potential slurry layer at the base of the inner core. So this is research that is largely funded by a NERC International Seed Corn Grant, which we were awarded for international collaboration and workshops in January 2020. Something happened shortly thereafter. Not very much international travel was possible for the next 12 months for this 12-month project. What we sort of flipped this into was an opportunity to try and build a model to look at what non-equilibrium processes might be important in the Earth's core. I'll explain what non-equilibrium processes are as we go through the talk. So yeah, this is work in collaboration with Chris Davies, Fred Wilson, and Mike Bergman at Simon's Rock. And yeah, it's funded by NERC. How do you get to the next slide? Like that. Okay, so some things you need to know about the outer core before we dive into any particular detail. It's liquid iron. I think you might know that already. And it's vigorously convecting. This is vigorous convection in a spherical shell of a conductive material that can lead and does lead to the formation of a magnetic dynamo, the geodynamo, and that's where Earth's magnetic field comes from. That is the process which protects the Earth's surface from a whole range of harmful cosmic rays, for example. This convection means that our sort of initial view of the outer core is it's homogeneous, well mixed. It's liquid iron at high temperature. It's got the viscosity of water. So think of this like a thick ocean, but it's made of metal. The inner core is growing, and as it grows, it forms solid iron that is purer than the liquid it's growing from. It's rejecting light elements, for example, oxygen, into the residual liquid, into the residual melt. These light elements are lower density than the ion they're being rejected into, and they therefore want to float. That's an important power source for the convection. So yeah, that's the sort of the starting point of any talk about the core. So geophysicists, especially seismologists, have an approach to, or sometimes have an approach that they see things they don't understand, so they give them letters. Bullen gave the Earth a bunch of letters a long time ago, in one of the first one-dimensional models of the Earth. Two of them we still use. For the base of the mantle, we call the base of the mantle D double prime. This might be post-perovskite in the lowermost mantle, it might be a phase change. That's not what I'm talking about today. What I'm talking about today is a thin layer just above the inner core, maybe 200 kilometers thick. Because we don't really know what it is, we maintain the nomenclature of Bullen. We call it the F layer. And the F layer is unusual, and it's been known to be unusual. It's a bit weird for since Bullen. It's unusual because it appears to be made out of different stuff, despite the fact it's within this apparently well mixed, strongly convecting, really vigorously convecting liquid shell. The way to think about this being a bit weird, a bit different, is to think about what happens to the P wave velocity in the outer core. For a liquid, the P wave velocity is really easy. It's the bulk modulus divided by the square root of the bulk modulus divided by the density. And our sort of one-dimensional models of the outer core assume, or some of our one-dimensional models assume, the outer core is well mixed. And if it is, our P wave velocity should follow a predicted adiabat. That's what PREM does. So provisional Earth reference model, this tens of thousands of times cited model of the Earth's interior. We have a straight line, straight dotted line. This is the straight black dotted line for those on Zoom. This is PREM. This is what you would expect if the outer core was behaving like I explained it behaves, like a convecting liquid. All our observations in more detail show that the outer core is the F layer, the lowermost layer, lowermost 200 kilometers of the outer core, is seismically slow. And that probably means that it is higher density. However, the outer core is growing, it's releasing light elements. Light elements have lower density, so the P wave velocity should go up compared to our reference. This is a problem for our understanding of what's going on just above the inner core boundary. Probably a problem with our understanding of how the inner core is growing. There are some models to explain this. Essentially, we need to get some dense material at the base of the outer core. The three existing models, three models that haven't been completely rejected that I'm aware of, are a model for inner core translation, a model for dendritic growth, and a model for a slurry. And we can actually, there are good arguments to reject all three models. So one idea is that the most unstable mode of convection in the inner core is a lateral translation. That means that on one side it's crystallizing, the other side is freezing. One side is melting, the other side is freezing. On the side that's melting, you're releasing basically pure iron. That's denser than the surroundings. That explains the F layer observation. Another model is that maybe the inner core is growing a bit like a snowflake. It's got these arms of solid iron that extend into the liquid outer core. We're then seismically sampling a mixture of solid and liquid, which is denser, and that might explain our anomalous observation from seismology. The third model, and the model I'm going to focus on, is that maybe the outer core is a slurry. Maybe we're crystallizing particles, crystals, pieces of iron above the inner core boundary. They're solid, they're denser than the liquid they're in, they sink. This is often called an iron snow hypothesis. We've got like particles of solid stuff raining out onto the inner core, and that could be the mechanism by which the inner core grows. It's growing by having solid fall on it and build its radius up, rather than direct growth on the surface. And that's what we're going to look at today. So arguments against all three models. Firstly, this translation mode of convection of the inner core isn't what you would predict from the latest estimates of the viscosity of solid iron under these conditions. That's a problem. These dendrites, it seems impossible to get them to be 200 kilometers long. They're probably going to break off. This could be going on close to the inner core boundary, but it's probably not explaining the whole signal. The problem with nucleation is we have to somehow find a way to form these little particles, these snowflakes, if you like. And as you might have seen, if you've been probing the inner core or the core literature, these there's a barrier. We'll come back to this. There's a barrier to forming a new solid in a large vessel of liquid, the core. And that means it might be very difficult to actually form the snowflakes, to have them grow and fall. Nevertheless, it's a story. It's a talk about slurry. It's a talk about how we can build a model of a slurry that captures the effect of nucleation and growth and things that allow us to treat the system as something that's not at equilibrium. We're not just going to read answers off the phase diagram. This is a problem that's not limited to the Earth. If you go and look in the literature of cores of other planetary bodies, you'll find a set of papers going all the way back to the 80s that make arguments for similar slurries to exist on bodies like Ganymede, on Mars, on Mercury, in different ways, in different places, depending on the pressures you expect. You can have slurries on the Earth where it's maybe just above the solid core. Slurries on Ganymede where you have a shallow layer. Maybe slurries on Mars. Maybe the reason Mars doesn't have a magnetic field is because the whole of the liquid core is a slurry, and it's got an inner core growing entirely by sedimentation, and this turns off the magnetic field, turns off convection, or overwhelms convection, maybe. So that's our background. It's worth thinking about this in terms of phase diagrams. I did mention phase diagrams, the slide or two back. The general idea is that in this layer, we are in a two-phase region of a phase diagram, of the iron light element phase diagram. The light element I'm going to be choosing is oxygen. If you've got another light element that you prefer, substitute it in your head. I'm going to work on oxygen because it's got the best model. It's got the best description under these conditions to describe what I need, which is actually the whole free energy surface. So if we just think about the black lines on this computer phase diagram, we are thinking that the F layer is somewhere like where the star is. So in this phase diagram, we've got a liquid regime. The amount of oxygen is on the x-axis, temperature on the y-axis. We're at 330 gigapascals, and we have a mixed iron oxide, iron oxygen liquid, solid iron region, and then below a eutectic, we have the whole thing crystallizes, and we have a mixture of solid iron oxide and solid oxygen, solid iron to freeze. So we're sat here. It might be easier to think about this in terms of pressure and temperature conditions of the Earth's interior. So here I've calculated. So the red line is an adiabat. This is what the temperature would do if we were vigorously convecting everywhere. Down to the inner core boundary. I've put the liquidus temperature for some bulk composition. I think it's 10%. Sorry, I think it's 5% oxygen in this plot. This is the black dotted line, and we are in this wedge of space where the solid and liquid is allowed to coexist. And of course, I think you probably all know, if we've got a phase diagram and we say everything's in equilibrium, what we're saying is that we have a liquid of some composition that has the same free energy as a solid, in this case, it's pure iron. And that's why we are tied, our liquid composition is tied to liquidus, and our solid composition is tied to the solidus, which in this plot is vertical. And we can apply the lever rule to work out how much solid and how much liquid we have. And you can, if you go back to, I don't know, it was a petrology course where I first saw this. If you imagine a piece of liquid crystallizing, so cooling down, you end up with the liquid, well, the liquidus, the solid inside until you crystallize everything and your liquid composition evolves. That's assuming that your system is always in thermodynamic equilibrium. If it's not, we'll see what happens. If it's not, your composition is allowed to depart from the liquidus. Because the only thing that says your composition is on the liquidus is that the free energy of the solid and liquid is equal. So what we're going to do is we're going to tackle this type of a statement that you find in all these papers about slurries in cores. Somewhere in there will be a statement that's similar to this one, which says, with our assumption that the precipitation is neither kinetically nor nucleation inhibited, this process will be immediate. That is careful wording that says we're in thermodynamic equilibrium everywhere. You find this in all the models. Question is, what happens if we lift this approximation? If nucleation is slow, if growth of crystals is slow, if these particles take some finite amount of time to settle out of solution, out of suspension. The other thing that's worth saying on this radius temperature plot is, what do we expect for an equilibrium slurry? For an equilibrium slurry, we expect the temperature to follow the liquidus in the slurry. We'll come back to that, but that follows from the composition following the liquidus. Okay, so that's the what is a slurry dealt with, and it's probably a good idea to tell you what we've actually done, what we've been doing for the past 3 years. Building this model that it captures the non-equilibrium processes. We're going to capture the non-equilibrium processes. One way to do it is to explicitly model the process of nucleation, the process of crystal growth, and the process of the crystal falling through the liquid that it's embedded in. And that falling is what's going to give us a timescale. So in the first part of the methodology, I'm going to describe how we build this model. And just this model by itself, imagining that a crystal forms, a crystal falls and grows, gives us actually some interesting, what I would say are interesting, some interesting insight into what a slurry might look like in the F layer or in other planetary bodies. And because we've got nucleation growth, we have this ability to depart from equilibrium. But the F layer slurry is not just one crystal forming things. The slurry is a whole population of crystals that form and sink. So in some way, we need to take this model and then capture something from it to build our model of a slurry. And that actually turns out to be straightforward. I'm hardly going to show you anything about that, except some results. But in doing that, we forget two things. We forget that as this crystal grows, it's rejecting oxygen. It's trying to change the composition of the liquid it's growing in. The other thing it's doing is it's releasing latent heat. So it's trying to change the temperature of the thing that it's growing in this liquid layer. And what we assume for now is that the layer itself isn't convecting, and it's losing this excess oxygen and excess temperature, excess heat by conduction. This gives us a way to solve the problem with the tools we've got. It turns out that maybe we can take this microphysical model and use that and parameterize it in a full convective study. But that's a project for later, not a project for now. So there's this final optimization to get the temperature and composition out, which we then need to use to compare with observations.
Sorry, that's a good question.
Yeah.
I think I understand how you do that to add latent production. How do you assess latent production?
So you know the growth rate of the solid. It's essentially the same equation. You know well, for us, none of the oxygen. One reason we've chosen oxygen is none of the oxygen goes into the solid. So if you turn a certain volume of initial liquid into some solid and some leftover liquid, all of the oxygen's got to go into the liquid.
Okay.
That's like an oxygen production rate on the surface, and it's the same conduction solution. So yeah, you get a term in a diffusion equation that's very similar to a latent heat term. I'm actually going to skip over that entirely at the end of the talk. Okay, so we'll come back to the thermodynamics. This is essentially why I chose the particular FEO thermodynamic model of Kobayashi, because we can't just work with a phase diagram. We need the free energy, or in particular, what we need is the difference in the chemical potential of iron in the liquid and iron in the solid, because the thing that's driving us towards equilibrium is the process of trying to make this equal to zero. That is the definition of equilibrium, when our chemical potentials are balanced. And we have this, so we have essentially an equation with some parameters, and quite a lot of parameters actually, that describe our free energy or our chemical potential. We can write down an equation to conserve oxygen overall, which is just a lever rule. If the lower x was x equilibrium was a composition of the liquidus, that would be what we're used to applying the lever rule. And we can work out the composition where the top equation, the 0 on the right hand side, is true. Plot that there, the yellow lines. Anywhere there's solid, we can calculate a solid fraction, and that's the shading on this phase diagram. So that's one of the things that's going in. That's driving us towards equilibrium, or telling us how badly the system wants to grow more solid to get towards equilibrium. So then the second piece of information we need is how fast does a crystal, or does a particle made of solid iron want to fall? Maybe a sensible starting point is just to say, well, it's falling it's Stokes flow. It's falling at the velocity that a solid particle would fall through a liquid. Mostly that's valid. That's our black dashed line on the left hand side. The problem is this Stokes flow solution, the balancing the force gravity essentially trying to pull the particle down with the viscosity of the liquid. That fails when the particle starts to move quickly. And it fails because you have turbulence set up around the falling particle. That happens when the Reynolds number gets above about 1. So the fluid dynamicists tell me. So to deal with this, we have to use an empirical law for the drag, the viscous drag, and that requires us to self-consistently solve for the Reynolds number and the falling velocity. It's a detail, but it means that our falling velocity is lower as our particles get bigger than we would expect as we get in towards this regime of high Reynolds. The other thing that happens is you get a mechanical boundary layer around the falling particle. We've got scaling laws for this. On the right-hand side, we're going to use these later. They come from studies of that are designed to look at microbes falling through the top layers of the ocean. But it's an analogous system. Everything's spherical, everything's moving through a stratified fluid. So that's one of our things we need to know. How fast do these crystals fall? We need to know how fast they grow, because we're going to want to know how big they get. How big they are determines how fast they fall. So something you might not know about metals is they can crystallize really quickly. They can grow really quickly when they start to crystallize. Partly that is because the nucleation barrier is quite high, so you end up cooling them quite a long way past their melting temperature before they start to crystallize, so you want to grow quite badly. That's the right-hand side of that top equation. The relation with the chemical potential. And what that says is if some liquid ion comes in contact with some solid ion, how likely is it to form a new solid? It's a thermodynamic term. But there's another reason that metals in general can grow quite quickly, and that's because the difference in crystal structure, the difference in structure, local structure between the liquid and solid isn't very much. So it seems that you really just need to adjust the liquid a little bit for it to become a solid. So this gives us, so that appears to be temperature independent. This gives us a relatively straightforward law for growth of pure iron, except we've never done the experiments at 330 GPa. And in principle, then we can calculate a growth velocity in meters per second of how fast a particular crystal wants to grow, depending on how big the difference in chemical potential is. If we're out of equilibrium, it wants to grow quicker or melt quicker to reach equilibrium than if we're very close to equilibrium. Now, we're not growing our iron particles in pure iron liquid. We've got this problem with the oxygen. And the way we tackle that is essentially to put this in the prefactor for our crystal growth. And we set up a little problem, a little diffusion problem around our growing crystal, where we say, well, we know the composition of the bulk liquid. We have a boundary layer, the thickness of which we know, because we know how fast it's sinking. We know the diffusivity of oxygen in liquid iron, and we assume the structure of the boundary layer is linear, because we've got to assume something. And we can use that to project the composition onto the interface, through the boundary layer, onto the interface between the solid and the liquid. And that gives us a composition on the interface. And that gives us a chemical potential difference, which tells us how fast the particle wants to grow. But that gives us an oxygen production rate, which we need to solve consistent with the diffusion part of the problem. What this means is our actual growth depends on the boundary layer thickness, which depends on the viscosity and how big the particle is and how fast it's falling. And it depends on the diffusivity of oxygen in liquid iron. And it depends on this unknown parameter K0, which is probably around 50. That is the growth rate that's the growth rate at very high temperature, essentially. And we have this change in behavior. You can see it best for the highest K0s, change in behavior from limited by reorganizing the structure around the liquid, around the solid particle, to diffusion controlled as the boundary layer gets thicker. which corresponds to bigger particles or more slowly sinking particles. So that's how we get our, so that also needs to be self-consistently solved. That's our equation for how fast particles grow. And what that leads to is actually quite straightforward. It's a pair of differential equations, pair of ordinary differential equations that are coupled together. Both of them have a self-consistent solution inside them, but that's fine because I'm not going to solve this with a pen and paper. This is going to be, or this is, solved numerically, and we can take a particular initial condition, so an initial height for a particle above the inner core boundary, initial size of the particle, and we can use our pair of ODEs to evolve that through time and watch how the particle sinks with time and how the particle grows with time and how these feed back on each other. And this shows that we can solve the ODEs essentially. What we actually want to do is look at how some of the parameters control this process. And the two most important parameters, or at least if we choose a temperature of the layer and initial size of the particle and how thick the layer is, and assume these particles nucleate at the top of the layer, which is a starting point. If we set that, the two remaining parameters that are important are the diffusivity of oxygen in the liquid and the viscosity of the liquid. So these plots are supposed to capture what happens if we assume our F layer is 200 kilometers thick. Our particles start very small, I think a nanometer, and they start off at the top of the layer, so 200 kilometers above the inner core boundary. We fix the pressure, we fix gravity, I think in this case. So gravity across the F layer changes by something like 20%. It's a place in the Earth where gravity changes a lot. And fix the oxygen content of the liquid. So we just have this layer of liquid iron with 5% oxygen at 5,000 Kelvin. With these little particle, or a little particle starting at the top, and we see how long it takes to fall, how big it gets for this simple case. On this side, on your left-hand side, I'm showing 5 cases. So this is height and growth rates against time until the particles fall out of the bottom of the layer. And they are mapped on the squares, with colored squares, map them onto on the right-hand side, which is showing how the two important parameters, oxygen diffusivity and viscosity, control the final size, that's the size of the spots, and the time it takes them to fall out of the layer. So can you see if yeah. So hopefully everyone can see the little hand. The first thing to think about is what happens if we change the viscosity. So changing the viscosity corresponds to following these lines of points from the left to the right-hand side of the plot. They all have, each line, the only thing that's different between each calculation is the viscosity. They have the same diffusivity, all the rest of the setup's the same. The first thing to see is as you increase the viscosity, it takes longer for the particle to fall. I think that's sufficiently obvious that I'm not going to explain why. But the thing that's maybe less obvious is that the particle size at the bottom, when it reaches the inner core boundary, hardly changes. And that's because our growth rate behavior, which scales as a boundary layer thickness, has almost the same scaling with Reynolds number as the falling velocity behavior when you do the scaling analysis. So what that's saying is that the growth rate trades off with the falling velocity, and viscosity isn't going to make very much difference, at least in this sort of broad parameter range, which is wider than what we think the the Earth is in, or the Earth's outer core is in. So what makes a much bigger difference is changing the oxygen diffusivity. So that's changing the color of the spots. Light yellow, fast oxygen diffusion, blue, slow oxygen diffusion. You can see that the particles, as you ramp up the oxygen diffusion rate, all you do is make the particle grow faster, just feed back on everything else. And that means that the particle grows faster, the particle gets bigger, the particle falls faster, and you have this big effect on both transit time and size. So you end up with much bigger particles and they fall much faster. And this exploration of our simple model, our model just of a falling particle, gives us an estimate of, broad estimate of how long a crystal is, a particle crystal is allowed to stay in the F layer. 3 days, 300 days. We prefer the lower end of that estimate. That we think is close to the parameters that we believe. And it also gives an estimate of how big the particles are. You know, in our total range of parameters, 3 millimeters to 1 meter, we think actually we're about a centimeter. We think if we were forced, we'd say we're here. That's why we've chosen this parameter range in the middle of the yellow one. Okay, so that's like the life of one crystal in the F layer. It forms somehow, it sinks, and it grows. Cool. So what do we do then? Well, we allow them to form everywhere. We allow them to fall everywhere. And because we know how fast they fall and we assume how often they nucleate, we can calculate the distance between the particles. And I can explain that in detail to anyone who wants to look at the integral that captures that. But it's essentially, if you've got two things moving at two velocities from two places, you can always work out how far apart they are. The thing we need to know is how often a crystal nucleates. And to do that, we use classical nucleation theory. This is another project we've got running, postdoc work with this project, Fred Wilson. And what this is saying is if you want to form a solid, you get a load of free energy back when you go from a liquid to a solid if you're below the melting temperature, but you've got to pay the penalty of having an interface. That means that there's a waiting time to form a solid, and we can work out how long that is. And that waiting time is our average time between nucleation events. And to calculate that, what do we need? We need the free energy, we've got that. We need the temperature, we've got that. We need the pressure, we've got that. And we need a prefactor, which is hard to know, but we'll see what we do with that later. We pick it. It's a more or less free parameter. We need a surface energy, which is well known. So what does this mean we can do? Means we can take a temperature pressure composition model of the F layer. We can work out how often everywhere in the layer you have these nucleation events, how big the initial crystals are. We can let them fall. And that means we can directly simulate the falling of all these particles. They're actually independent of each other when they fall. We assume they're independent of each other when they fall. And that gives us a particle size distribution plot. So this is a histogram of how big the particles are at each layer of radius as a function. So it's how many particles we have of each size bin, essentially. Do we have mostly small particles near the top, mostly big particles, but with a nice spread of small particles near the bottom? That's fixing the temperature and composition.
That's a question.
Yeah.
Because you point out the growth rate, 16.1 kilometers per million years. I mean, your Earth is 4.5 billion years old, and 1 billion years.
Yeah. So this is one of the things we can use to decide whether to reject or accept these models. A reasonable estimate for the inner core growth rate is about 3. kilometers per million years. It depends when you assume the inner core first formed, which maybe is 500 million years ago, maybe a billion years ago, maybe 250 million years ago. There's a lot of debate about that number, and that feeds through to our sort of acceptable growth rate. So this would be growing slightly faster than what is acceptable. However, we're not allowing the layer to evolve. So we're not capturing at this stage. We're not capturing the heat, the latent heat production, which is the next step. So the next step is to capture latent heat production. There we set our temperature at the top, which is set by convection of the core. We assume that all of the crystallization happens in the layer. We have nothing growing on the thing. That means that on the inner core boundary, that means we've got a zero flux condition, and that's a boundary value problem. Again, for an ordinary differential equation. We end up having to solve that iteratively. That gives us a temperature. We're balancing now. For each time we reevaluate this model, each time we update our temperature profile, we recalculate the whole crystallization everywhere, growth and falling everywhere. Which means we get out a temperature profile. And don't want to overrun, I'll skip through this relatively quickly. So one of the things we can do is we can use our free nucleation parameter, our prefactor for nucleation, almost as a dial to go out of equilibrium, allow it to come to equilibrium, because this nucleation parameter is the least well known and has a lot of leverage over how easily we get to equilibrium. High nucleation rate allows us to reach equilibrium easily. Low nucleation rate, zero nucleation, we're never going to be in zero nucleation, never going to be in equilibrium, right? And what comes out is the temperature. So given our diffusion, our assumption of diffusion of heat through the layer, if we're not generating any heat in the layer, we're not putting any heat in the bottom of the layer, our zero nucleation solution is necessarily isothermal. It just matches the temperature at the top. And then if we allow nucleation to be really fast, we get a solution which more or less follows our liquidus, which is what we expect for the equilibrium case. And in between, somewhat to my surprise, we find solutions where the temperature profile is in between the liquidus and the no crystallization state. And for each one of these solutions, we have the full crystal size distribution, which I think is on the next slide. This is highlighting some parts of that plot. So for one of these solutions, we end up with a nucleation rate. Turns out that nucleation is mostly in the middle of this regime, where we have a big uptick in our small particles, and then you see that sort of propagating time down to the inner core boundary. And this particular model gives a too low growth rate. This is the bottom end of what 0.1 kilometers per million years, the bottom end of acceptable. So that's more or less the whole story. So what do I want to conclude? So I think the first thing I want to conclude is that if a slurry exists, I'm not saying it does exist, but if it exists, we would predict sort of millimeter to meter sized particles, probably centimeter, close to 1 centimeter in the slurry. So these are not going to be directly observable seismically. We have this range of falling time, which is not seconds, it's not millions of years, and the particle density is really low. So all of these plots gives a really low particle density for the slurry. So 1 times 10 to the minus 2 particles per meter cubed. I hadn't worked that out before this morning. That's about 4.5 meters between our particles. So we're thinking like small pebble-sized particles falling through the lowermost 200 kilometers of the core, and they're separated by 4 meters on average, if a slurry exists. And then the other things we've done really is think about how, which I guess is kind of the point of a proof of concept seed ground. Thought about how we would go about building a full model of non-equilibrium fluid dynamics for a slurry in the base of the core. The first thing we worked out is that actually we can never get to equilibrium because it gets harder and harder. The driving force towards equilibrium just goes away eventually. I guess you can get close enough to equilibrium that it doesn't matter. Of all of the things that, of all the kinetic effects that are important, nucleation is the one that matters most. And yeah, we would, in principle, we have the equations. Don't think we could do it in a practical calculation, but in principle, we have the equations to allow convection in this layer by tracking a crystal size distribution in a convective simulation, though that is probably beyond what can be calculated. So that's all I wanted to tell you. I'm happy to take any questions.
Right. Toby.
Always ready to ask a question, you know.
There are no stupid questions, Toby.
Yeah, well, you know, you'll have that. That's not true. So the inner core, as you accumulate more material to it, the surface area of that's going to increase. So the rate is going to change over time. You've got more area to cover.
Yes.
As this keeps accumulating iron, is it getting new sources of iron into the slurry, or do you think the slurry eventually sort of freezes off when you've got no new material coming in?
So this is happening at the base of just in the lowermost part. The way we've got this set up is we're assuming that the layer evolves quickly enough that it always follows the behavior of the bulk of the outer core. That's why we have the boundary condition at the top. So we, in principle, if we wanted to know what was happening to the rest of the outer core, what we would do is we would start from an initial guess at what was going on, do the calculation for the layer, the F layer. That gives us a heat flux and an oxygen flux out of the top. That would have to go into some sort of, maybe just keep track of the total oxygen content in the outer layer. Balance heat flux across the core mantle boundary, probably, and then recalculate where the liquidus and the adiabatic cross, so update the bottom and redo the calculation. And we're making this assumption that the core state, the outer core state evolves slowly compared to the layer state to do that. Does that sort of answer?
Sort of answer, yeah. So how rigorous is the convection in the
We don't know. In the model, we're assuming it's not convecting at all. It's all diffusive. Yeah, they settle. In principle, if you know the flow velocity of the liquid, I think you can then sort of correct, you can apply that to the falling velocity of the particle, and maybe the liquid's moving up faster than the particle's falling downwards, so it would move upwards. And it depends on the size of the particle, so if you have a range of different particles. Yeah, I've not really looked at that. There are attempts in the literature, and there's some ongoing work in Leeds trying to look at the proper dynamics of a slurry. I did look at the mathematical description of that, and yeah, left that to the postdoc who was dealing with it. Okay, cool.
John?
I have a very simple question. I'm not a geophysicist. Where is the snow coming from? Is it coming from the inner core? Is it part of the convection, and it's just coming back to the inner?
I think the idea would be that you you've got convection in the outer core, but the bottommost layer of the outer core is below the liquidus for the outer core. So a parcel of liquid flows across this liquidus layer, and that's where, because you're now below the liquidus, that's where the snow comes from. It comes from like crystallizing the liquid as it crosses that boundary.
Are you saying that once it kind of settles on the core boundary, it doesn't, that mass doesn't get recycled back?
No, yeah, it falls out, it grows, and that's why the core grows, or how the core grows. At least that's one end member of how the core, the inner core might grow. The other end member is it's like directly growing by crystallization on the boundary.
Yeah, the other models for sure.
Yeah, and you could have something in between.
So just follow up, is it snowing on the inner core year round everywhere?
Yeah. In this model is one dimensional and time independent. But yeah, no, I think in the models that exist, yes. In reality, if we've got this flow, we've got this complicated convective pattern, it might be more like a complicated weather system.
Yeah, is that an assumption of your model?
Yeah, it's an assumption. It's an assumption.
So I have a quick question. I'm not sure if you mentioned it when I missed it, but sort of at the inner core outer core boundary, right? We have the effect of gravity is really important.
Yeah.
So how is that affecting this interplay of nucleation in terms of particle size and things like that?
So gravity feeds into the falling rate, and that's the only place it enters. For the simple layer calculation, we just set gravity. We just have a constant. Right. But for the code is set up, and we use this feature of the code in the self-consistent solution, the final solution. It's set up to handle radially varying gravity. So what we actually do is cheating a little bit. We take Prem and we use gravity from Prem. So we use a 1D gravity profile that isn't self-consistent, isn't consistent with the density, but we're talking about tiny little density variations, right? What matters is how close you are to the inner core.
Right.
So it's not quite self-consistent. We'd have to solve a whole Earth model every time step, and we're not doing that.
Hi, Andrew. It's fantastic talk. Thank you so much. It's so fascinating thinking of the snow of Ireland. I have a question that comes to me because I have the same problem when I manage to write a grant, which is impact. Mm-hmm. So you said you were successful with NERD, so congratulations. What did you write on those 2 pages?
So this was an international collaboration seed corn grant. So we could write about the importance of international collaboration for building international collaboration for strong science in the UK, and how that was important for the national economy. It's so, strictly speaking, I think that's what we did, actually. I think that's essentially the argument we put, but it's so clearly curiosity-driven science that any panel that goes along and says this wouldn't fly for an episode panel. No chance this would fly for an episode panel.
Was it iron snow?
But yeah, we essentially said this is curiosity-driven science, and it's got international collaboration, and that's the point of the scheme.
Sorry, I didn't want to be a cheeky question. It's just like...
Yeah, no, it's a fair question. So I sort of think this is away from the topic of the talk. But I sort of think when there's something, when the research is clearly potentially impactful, there needs to be some way to identify that. When it's clearly curiosity driven, that's why we have, that's why we're lucky enough to live in a country with higher education institutions. And yeah, just I say that and see what happens.
You're saying it has to be more effect on people with velocity, basically.
We've not done the full calculation of that. It's there will be because of the changing oxygen content, but it's not going to be big enough to see.
I feel like glass.
Do you have any?
I saw it. Yes.
So, in terms of the process, would you expect there to be any signature on within the core? So I could imagine if you've got this snow falling, you would expect some sort of radial structure, whereas if it's growing with these fingers out into the core, you would expect some sort of unusual.
Yeah. So
it's
there's a lot of studies of seismic anisotropy of the core, of the inner core. So I think we'd expect some sort of signature in the 1D seismic velocity of the outer core, and there is some sort of signature. We've not done a direct comparison. I suspect the biggest signature we'd see in the inner core was a change in attenuation. If we've got essentially a sedimentary rock, presumably infiltrated with a liquid, sort of like an icy slush. In fact, it might be it is a slushy. At the base, it's a slushy layer, not a slurry layer. That can have all these processes of what they call it melt squirt and all these processes that attenuate seismic energy. Whether they're different processes than to what you get if you've got dendritic growth going on or not isn't very obvious. Maybe this layering would be preserved at depth.
This one to chat.
You have a go for it.
So, in geoscience, you always based upon we use one model to explain everything, but do you think it's a mixture of these three models that you show?
I think it might, yeah. I certainly don't have a problem with the idea that it might be a mixture. I think if there's direct growth on so we have this growth parameter, and I'm assuming that it's by sedimentation. One way of thinking about another model is to say that sedimentation is only a fraction of the growth rate, and then something else can explain the rest. I would struggle to have the lateral translation and melting on one side with the slurry. I think that might be difficult, but the dendritic growth and the sedimentation could certainly happen together, and that means we have some unknown factor to divide the two growth contributions to growth up. Yeah.
Excellent. If there are no more questions, let's thank everyone again. Stop sharing.